হ্যাঁ, মানে ট্রেডমিলে হাঁটতে হাঁটতে হার্ট অ্যাটাক হয়েছে, অল্প বয়স, 22-23 বছর বয়স।
মানে আমার মনে ওভার স্ট্রেন কিছু কম নেই, যতটা লিমিটের মধ্যে আছে।
বিশেষ করে ট্রেডমিলটা খুব ডেঞ্জারাস, মানে
হ্যাঁ, মানে কি হয় যে কি হুট করে আমরা স্পিড বাড়াতে থাকি, মানে আমিও যখন করতাম তখন হুট করে আমরা স্পিড বাড়ানোটা শুরু ইয়ে থাকে
একদম। আর দ্বিতীয় হচ্ছে যে ওখানটা তোমার যদি মানে এক্সপিরিয়েন্সড ট্রেনার না থাকে, খুব মানে খুব সমস্যা আর কি,
হিতে বিপরীত হবে,
একদম হিতে বিপরীত হবে। মানে হার্ট ওভার স্ট্রেইন হয়ে গিয়ে হার্ট আর রিদম রাখতে পারবে না। এবং বহু মানে অল্প বয়সী ছেলে, মানে তাদের মধ্যেই তো
রিসেন্টলি সিদ্ধার্থ বলে একটা ইয়ে ছিল, অ্যাক্টর ছিল, মানে নরমাল টিভি সিরিয়ালই করতো উনি।
ওর কথা। তারপরে এই যে রিসেন্টলি মারা গেল কর্ণাটকের একজন, ওই আপু বলে একটা সিনেমা হয়েছিল, তার অ্যাওয়ার্ড উইনার, ন্যাশনাল অ্যাওয়ার্ড উইনার। ওর বাবাও খুব বিরাট বড় মানে অ্যাক্টর কর্ণাটকের। মারা গেল ওই একই ভাবে, সকাল 11টায় ট্রেনিং, তার আগের দিন রাত্রিবেলা পার্টি করেছে, এত পার্টি করেছে যে খুব টায়ার্ড ছিল। এবার পরের দিন সকালবেলা 11টায় বাড়িতেই জিম করছিল, ব্যাস জিম করতে করতে হার্ট অ্যাটাক, মানে রাত পরে ডাক্তারের কাছে নিয়ে যাওয়ার সাথে সাথে সেখানেই কোলাপস করে গেছে। খুব ডিসঅ্যাপয়েন্টিং। মানে সেটাই সেদিন একটা খুব লম্বা হোয়াটসঅ্যাপ মেসেজে দেবী শেঠী বলবার চেষ্টা করছিলেন যে মানে এত শরীরকে এত কিছু করার কোনো দরকার নেই, আর এজ হলে পরে এজিং হবেই, এটা কেউ অ্যাভয়েড করতে পারে না। হ্যাঁ, সেই। সুতরাং ওই এজিংটা হচ্ছে নর্মাল প্রসেস, বডি তো ডিটেরিয়েট করবেই না। এখন যদি আমি বলি যে আমার তোমাদের মতন বয়সে আমার এনার্জি যা এখন আমার তাই এনার্জি, তা হয় নাকি কখনো? হতেই পারে। আচ্ছা চলো তাহলে, অনেকক্ষণ গল্পটা কাছা করলাম। তোমাদের তো কালকে থেকে ছুটি না? কালকে থেকে বোধহয় ছুটি শুরু।
স্যার দিচ্ছে কি ছুটি? মানে আপনাদের কি বলেছে? আপনাদের ছুটি মানে আমাদের ছুটি হওয়ার কথা।
হ্যাঁ, মানে ইউনিভার্সিটি তো ছুটি ডিক্লেয়ার করেছে 4 থেকে 6, 7-8 তো
ও তাহলে তো ইটস গুড।
হ্যাঁ, 7
তাহলে এমনি পেয়ে যাচ্ছি ছুটি। ও দেন ইটস ওয়েল এন্ড গুড, তাহলে তো সব ক্লাসেসই অফ হয়ে যাবে, অসুবিধা নেই।
আবার অনেক ক্লাস, যেমন আমি কালকে ইলেকট্রিক্যালের ফার্স্ট ইয়ারদের ক্লাস দেব, মানে ওরাও রাজি, আমি বললাম সব ইঞ্জিনিয়ারিং মেকানিক স্টার্ট হয়েছে, সুতরাং ওদেরও করবো।
স্ট্যাটিক্স পোরশনটা আপনি দেখছেন?
স্ট্যাটিক্স না, স্ট্যাটিক্স ডাইনামিক্স দুটোই পড়াতে হবে।
ও আচ্ছা আচ্ছা আচ্ছা।
আচ্ছা, তাহলে আস্তে আস্তে আমি রেকর্ডিং এ যাই। আমার আজকাল আমি ইলেকট্রিক্যালের রেকর্ডিং করতে গিয়ে দেখছি ইনিশিয়াল ভিডিও কিছু আসছে না, কিছুক্ষণ বাদের থেকে তারপরে ভিডিও। কেন হচ্ছে কে জানে। তা আমি কিছুক্ষণ অটো অ্যাডমিটটাকে অফ করে রাখবো, নাহলে এটা হতে পারে। আচ্ছা
আচ্ছা আচ্ছা আচ্ছা।
অটো অ্যাডমিটটা অন থাকলে পরে এ হয়, চালু করে দিয়ে তারপর আবার চালু করতে হবে। Let's see what happens. So students, so today as we were dealing with the situation, we have been talking about the rigid body kinematics, and so far we have discussed the what is called as the relative velocity method, relative acceleration method, but all those things were discussed in connection with a non-rotating reference frame. Today we will pick up more general theory of relative velocity and relative acceleration. This is with respect to the rotating reference frame. That means all the relative velocities and accelerations will be measured with respect to a reference frame which is rotating one. So in this method, it is actually more general description of the relative velocity and the relative acceleration analysis. So in this method, what we have a reference frame that is mounted on a rotating rigid body, and the relative motion of another particle. So either it is rigidly mounted on a rotating rigid body, and the relative motion of another particle is being observed from that rotating frame. So that can be one possibility. That means, in order to explain this, let me just introduce one page here, that what is actually meant by that. Now, what I see by this, what I mean to suppose is that, say, let us consider that we have a rod, correct? This rod is being, pivoted at this point, and the rod is rotating with some angular velocity and some angular acceleration. Say this is omega, and let us suppose that this is omega dot. Okay, so now we consider on this rod a slider. Suppose we have a slider. Okay, now this slider is having a relative velocity. Say either this slider can move in this direction, or it can move in the downward direction also. It can have, alternatively, it can have the downward motion as well, correct? And this also can have the angular velocity can be this way or that way, angular acceleration can be this way or that way. The velocity with which the slider is moving on this rod, that can be also upward or downward like this. And you see that if you want to calculate, right, the velocity of the point A, which is belonging to this slider, so what you need to do, you need to actually, consider, a reference frame, right, which is to be mounted on this rotating rod. Let us suppose that we place a reference frame. Say this is the reference frame x-axis, and this is the reference frame y-axis. The origin of this reference frame is here at this point O. And this reference frame x and y is rigidly connected to this rotating rod. Now a person who is standing with the reference frame at its origin, and let us suppose that this is the inertial reference frame, capital X, capital Y, suppose. Or it can be, say, let us suppose that the inertial reference frame, let us define it in this way. Suppose we have the inertial reference frame is this, capital X and capital Y. So this inertial reference frame means their orientations will remain the same in this direction. And this small xy, that means we say capital XY is inertial frame, and small xy is the rotating frame. This is the rotating frame. Okay, so this small xy, if it is directly rigidly connected to this rod, then we see that the angular velocity of this rotating reference frame must be equal to omega, and omega dot xy, that must be equal to omega dot, or we can write it to be equal to alpha. Now, in order to calculate this point A, right, its velocity or its acceleration, you see that your distance between this O and A, it is continuously changing. Why it is so? Because this slider is moving relatively to this rod. So naturally the distance between OA, so the distance between OA is not constant, which was the case, for any rigid body. Say any rigid body which is rotating, if we take on the rigid body 2 points A and B, we know by the definition of the rigidity, the distance between them is always going to be constant. However, in this case, the distance between the point O and A, right, this distance is not constant, and in order to calculate the velocity and acceleration of this point, you need to consider the rotational motion of the reference frame, and that's why this velocity with which it will be moving is termed as the relative velocity. That means this red vector, correct? This red vector is the relative velocity of this slider with respect to the rotating reference frame x and y. So in order to calculate its absolute velocity, that means if the person is standing on capital X, capital Y axis, capital X, capital Y is inertial frame. So any person who is standing in this reference frame will measure the absolute velocity and absolute acceleration of this point. So that is why, you know, in order to calculate this absolute velocity and absolute acceleration of this point, which is relatively moving in a rotating reference frame, we need more generalized definition of the relative velocity. So that is what I try to say here, that in this method we have a reference frame which is rigidly mounted on a rotating rigid body, and the relative motion of another particle is being observed from that rotating reference frame. For the sake of simplicity, for the sake of generality, we actually consider capital XY as the inertial reference frame and small xy as the non-inertial reference frame, that means the rotating reference frame. For example, this is capital X, capital Y axis, and this is small xy axis. This one is inertially fixed, and this one is, you know, it is connected with the body, just like we showed in the example that we attach this xy reference frame to this rotating rod. Like that, we see that this xy axis, it is attached at the point A and it is allowed to rotate. কারো একটা না mic on আছে, হ্যাঁ, please mic-টাকে off
Hiran, please turn off yourself.
একটু মাইকটাকে অফ করে রাখো, নাহলে তোমার সারাউন্ডিং নয়েজ ঢুকে যাবে। So you will see that we have therefore this xy axis is it is rigidly connected to this rotating body with point A. But for more general definition, let us assume that this reference frame is having an angular velocity. This reference frame is having the angular velocity which is, you know, something different, which is something different than you know, the absolute angular velocity of the body. So this we have intentionally done. That means I bring another angular velocity, capital omega xy. This, suppose if this reference frame is you know, if it is absolutely fixed, if it is absolutely fixed to the body, just a minute, control, yes, let me just change my color. Yes, now we see from here that if we try to, you know, bring this absolute angular velocity here, this omega xy, capital omega xy, this capital omega xy is actually not equal to, you know, the omega of this body. This is done for more general purpose. However, for this example, in this example, you see here we have attached this reference frame rigidly to this rod, and as a result omega xy is equal to omega of the body. But here to give more general outlook, let us assume that this omega xy, I need to say capital omega xy, and the small omega, that means the absolute angular velocity of the body, they are different. They are different. We are not assuming them to be equal. They can be equal or they may be different. But here we have assumed it for more general formulation. We have assumed this to be unequal. So because, you know, this inequality between the two angular velocities will be more pronounced when you will be discussing in your next semester the three-dimensional motion of the rigid body. Correct? Three-dimensional dynamics, when you will be going to discuss it, there you will come across that how your these two angular velocities can differ. but we are not going into this discussion right now because we don't have this scenario in our plane motion. So we see therefore in this case, let us consider, however, for more general description, I retain capital omega and small omega and make them unequal. So if we consider another body, another particle B, which is having the relative motion with respect to this point A, and as seen from this rotating reference frame small xy axis. Now, if I consider this position vector as rho bar B relative to A, which is actually the position vector between these 2 points, then I can write this equation, that is the absolute position vector of this particle B is equal to the absolute position vector of the particle A plus the relative position vector of B relative to A. Now, if you differentiate this with respect to time and that too with respect to capital XY axis. Now, this is very interesting. That means this differentiation is done with respect to the inertial reference frame, because here we are using two different reference frames, so we need to be careful that the differentiation is done with respect to which reference frame. So here we are doing the differentiation with respect to the inertial frame. So if you differentiate, all differentiation will be something like this. Obviously, this differentiation will lead to the velocity of point B, and this differentiation, I mean to say dr bar A dt with respect to capital XY will give you the velocity of point A, and this will be the differentiation of this position vector with respect to capital XY axis. Correct? Now, you see, as I have told you, that if the point B is having the relative motion with respect to point A, how it can happen? I have given this example. If you imagine this point O as point A and this point A as point B, that means instead of calling this as O, if I call it as point A, and instead of calling this point A, if we call it as point B, as we have shown in this case, this rigid body is basically the rotating rod. This rotating rod is that rigid body, and the point A is actually our origin, and point B is actually the slider point. So you see, therefore, the distance between these two, is continuously changing. So as a result of that, you see, this position vector is not constant. So therefore, in order to actually find out its derivative with respect to the big XY reference frame, what we need to do, we need to change first the coordinate axis. That means what we need to do is that we first try to calculate the time rate of change of this position vector with respect to an observer who is standing on this small XY reference frame at point A. Please note, a person, say like this, is standing here. Say this is a person, he is standing at point A on the reference frame XY and is trying to measure how the point B is having this position vector is changing with respect to time. So I have this d rho bar B relative to A dt xy. Physically, this derivative means the relative velocity of point B with respect to point A as seen from the rotating reference frame. This you need to clearly understand. So this is therefore, the magnitude derivative, because you see, when you are trying to calculate the time differentiation with respect to big XY, that means what a person who is standing on this reference frame, on this reference frame, I mean to say on the inertially fixed reference frame, what he will observe? He will observe that both this magnitude and the direction, both are changing with respect to him. However, the person who is standing on this rotating reference frame, since he is rotating, for example, in this example, the person who is standing in the small xy axis, since this small xy axis is rotating as this rod is rotating also with the same angular velocity. So what the person is recording? He is seeing only this magnitude change, the magnitude is changing. He is not recording any change in direction. He or she is not going to record any change in direction, because the observer is also rotating with respect to the body. For example, if you are on the earth, what you will find? That your home or your neighbor's home is always along a fixed direction. You will not see that tomorrow your neighbor's house is who is actually your neighbor, suppose, is residing on the eastern side of your house, and tomorrow when you will wake up in the morning, you will again see that the neighbor's house is towards the eastern side. You will not see to that on the next morning when you wake up, you never see that your neighbor's house has changed its location from east side to west side. But an astronaut who is in the space, say for example International Space Station, say ISS, a person who is there in ISS, let us assume that that particular person is an inertially fixed reference frame. Let us assume it. So what that ISS person will record? That ISS person will record that today your neighbor's house is towards east with respect to you, but tomorrow it will be in, or after time delta t, it will be in some other orientation, because he is actually observing two particles who are fixed on a rotating frame. So therefore, with respect to him, he or she will see that both this magnitude and this direction is changing. But the person who is situated on this rotating reference frame, he or she is just observing the change in magnitude, the distance between them. So therefore, there are two concepts. The differentiation is to be done with respect to the magnitude, and the differentiation is to be done with respect to the direction. So both these two differentiations will be done when you are differentiated with respect to the inertially fixed reference frame. So as a result, this derivative will have two components. One is this component, which will take care of only the change in magnitude, and this is the component which will take care of the direction change of this vector. So how the direction change in vector is obtained? It is obtained by taking the cross product of the angular velocity of the reference frame with this position vector. How this comes? Let us explain this with an example. Here I have tried to show you. Suppose this is the rotating reference frame and this is the vector. Let us say this is your vector AB bar. That A bar represents your position vector B relative to A. So let us call this as our A bar vector. Now at any point of time, this A bar can be written as AX I cap plus AY j cap. So when you are differentiating this vector with respect to the inertial reference frame, basically you are doing this differentiation. Now if you see this differentiation, when we are breaking up this differentiation, you see that this differentiation is dAx dt with respect to big XY I cap plus dAy dt with respect to XY, that normal differentiation. But not only this differentiation is there, but also you will be having differentiation of this unit vector with respect to the inertial frame as also you will be having differentiation of this j cap vector with respect to the inertial frame, so that we can move on to the next page and can see that we can have the other differentiation here. We can have this other differentiation there. So you see that, therefore, actually in between I have inserted this page. So forget this existence of this page. So we are actually continuing from that previous to previous page. That means we are continuing from here. So we see that if we differentiate, this with respect to your capital XY, then we see that the complete differentiation will look like this. So you see that I can now, since it is a scalar quantity, Ax is a scalar quantity, the scalar quantity differentiation does not depend upon the reference frame. That means if you have a scalar quantity, the differentiation of that scalar quantity will be the same, whether you are doing it with respect to an inertial frame or whether you are doing it with respect to a non-inertial frame. So therefore, dAx dt, which was earlier done with respect to capital XY, it is written capital XY. Now I am changing it to small xy because it is scalar. Similarly, this is done for that. And then you know that from your knowledge of r theta coordinate system, you know that when you are differentiating a unit vector or the normal tangent coordinate system from your particle dynamics analysis, you know that if you differentiate the unit vector, actually the unit vector differentiation result is this. That means you need to take the cross product of the angular velocity of the reference frame with respect to that I, and similarly this will be done with respect to j. So the angular, so this is these two results, that means this represents your I cap dot with respect to this dot, means this is actually d I cap dt with respect to capital XY, correct? Similarly, this one actually represents j cap dot. So I cap dot and j cap dot can be written just by taking the cross product of the angular velocity of the reference frame with that vector. So you see, this is x, this plus ay. This we have already seen in our particle dynamics section when we discussed the normal tangent coordinate system and when we discussed the subsequent r theta coordinate system. If you recall that, you will see that the vector multiplication is something like this. So it means that I can club these two together and can say this is dA bar dt small xy, and if I take this, then I can take that it is omega xy cross this vector. So the most important conclusion is what? If you take any vector, let us say a bar is an arbitrary vector. If you try to differentiate it with respect to the non-rotating reference frame or inertial reference frame, that derivative is equal to derivative of the same vector with respect to a rotating frame plus omega bar xy, that means angular velocity of that reference frame cross with this vector a bar. This is taking care of the magnitude derivative and this is taking care of the direction change of the vector a bar. Okay, so if you recall that, then as I have told you, also that this vector that you are getting, this vector, it is what it physically represents the relative velocity of the point B with respect to point A as measured in a rotating reference frame, and then you have this extra product. So as a result, what you get from here, that we can write V bar B is equal to V bar A plus V bar B relative to A xy plus omega bar xy cross rho bar B relative to A. If we tell them in words, if we describe them in words, V bar B represents the velocity of any point on a rotating frame is equal to velocity of point A, where the point A belongs to the same rigid body where you have put that frame, rotating reference frame. This represents the relative velocity of the point B with respect to point A as measured from the rotating frame, plus this is the extra term that you are getting. So this is sometimes known as the three-term velocity equation. Now you see, if I say that this equation is more general. Why I say it is more general? If you do not take your reference frame as as a rotating one, then you can drop this idea, correct? And suddenly the velocity will become, the relative velocity will come to this equation, which you have known, studied it earlier in your physics. Also we have studied it with respect to a relative velocity equation when we are dealing it with respect to a non-rotating reference frame. So that's why this is the more general description of the relative velocity equation that is done with respect to a reference frame which itself is rotating with respect to an inertial frame. So this is what is called as, sometimes is known as the three-term velocity equation in physics. Now this is actually known as the velocity analysis, obviously, because we have framed the velocity. Now we can go for the acceleration analysis. That means what we do, we differentiate it again with respect to the inertial frame. All differentiations need to be done with respect to the inertial frame. So you see, this will be all, the derivatives will be something like this, just a simple differentiation of all the terms. But please note, this relative velocity is, is done with respect to a rotating reference frame, and now you are trying to differentiate it with respect to a inertial reference frame. So there is a mismatching between the two reference frames. So what I need to do, again, I need to differentiate this vector with respect to the rotating frame, plus I take care of its, what is termed as its change in direction. Exactly in a similar manner, we need to differentiate this equation also with respect to the, because this vector is actually in a rotating frame, but we are trying to differentiate it with respect to a inertial frame. So again, a mismatch is there, because this position vector is actually in the reference frame small xy. So again, this mismatching is there. So again, we need to take care of the magnitude derivative and the direction derivative. So here and here, these two things need to be done. Others are same. That means what we can do now, if we just expand it, then I will be getting, this will be giving me acceleration of point B. This one will give me acceleration of point A. Now I differentiate this V bar B relative to A xy with respect to the reference frame xy. I mean to say with respect to small xy, correct? And then I take its direction change derivative. Just like the vector we have seen, any vector which is there in a rotating frame, it follows this rule of differentiation. So now in place of A bar, you think the vector B bar B relative to A. So in place of A bar, you just substitute vector, because here A bar can be any vector. Yeah, so it may be a position vector, it may be a velocity vector, it may be an angular momentum vector, whatever you can think of. So you see, you just insert in place of A bar this V bar B relative to A, and you will get, following this theorem, you will get this equation. And then you have this term is unaltered. Again, you have, this position vector. So again, put in place of A bar, put rho bar B relative to A, B bar relative to A in this equation, and naturally you will get this big term. That means you will be having, the omega bar, the term here. That means omega bar xy cross. You have an additional multiplication here this is an additional multiplication. So just think of d dt of rho bar b relative to a xy. That will be equal to d rho bar b relative to a dt small xy plus omega xy cross rho bar b relative to a. And since you have a pre-multiplication of this vector, so ultimately omega bar xy will be multiplied all through. So I think you have understood the thing. Actually, you know, this differentiation, the d rho bar dt. So if you just I can write it here that this differentiation is basically equal to d dt of so this differentiation will be d dt of rho bar b relative to a small xy plus it will be omega bar xy cross rho bar b relative to a. Now since you have a pre-multiplication by this omega xy, so omega xy will be pre-multiplied to this vector, omega xy will be pre-multiplied to this vector. So as a result, you have this term, you have this term, and then pre-multiplication will give you this term. So you see, this is how you can have the entire scenario. You can have this entire scenario. Okay. So this is how you are getting the thing. So now if you simplify, this is a big term. Now if you simplify, the simplified form will be something like this. It will be a bar b, that will be equal to a bar a plus it will be a bar b relative to xy, because you are differentiating the relative vector with respect to the rotating frame. So this will be the acceleration, relative acceleration of point B with respect to A in a rotating reference frame. Then you have omega xy cross v bar b relative to A, and here another v bar b relative to A will come because you are differentiating it with respect to xy. So there are two such terms. One is here, another is there. So these two clubbed together will give you this term, which is nothing but known as the Coriolis component of acceleration, about which we have already studied in our r theta coordinate system. So always remember, the Coriolis component of acceleration comes into the picture whenever you are having a relative velocity with respect to a rotating frame. That's why any earthly motion, motion of the wind, motion of the wave, sea wave, motion of the river waves, right? All these are actually affected by the Coriolis acceleration, and thereby it gives various, you know, various natural geographical phenomena. Just like, you know, the the cyclones in the northern hemisphere will always rotate in the counterclockwise sense, while, you know, the southern hemisphere, the cyclones will always rotate in the clockwise sense. Again, the water will circle down to your pipe from your basin in the northern hemisphere in an anti-clockwise manner. The vortex motion will be anti-clockwise. While if you go to any southern hemisphere country like Australia or Brazil or South Africa, something like that, and if you actually wash your mouth on the basin and allow the water to flow through the pipeline, flow to the valve, you will find that that rotation, vortex motion will be clockwise in nature. হ্যালো, তুমি আমাকে একটু পরে ফোন করো, আমি ক্লাসে আছি। হ্যাঁ, ক্লাসের পরে কথা বলবো। তুমি 12টা নাগাদ আমাকে ফোন করো, 12টার পরে, 12টা 5টা নাগাদ। Okay. So we have, therefore, we know that we get that this is the Coriolis component of acceleration, and you get this is the thing, and then you have omega bar dot xy cross rho bar b relative to A, and for plane motion you know that this term can be simplified too, but again please remember this is only applicable for plane motion. This is not going to be written, I mean to say this minus this term, you know, it is applicable for only plane motion. 3D motion you cannot simplify to this. For 3D motion you have to take your equation in this manner. I mean to say it will be omega xy cross rho bar b relative to A. No further simplification will be allowed in 3D motion. Please remember it. Don't make such mistakes when you will be in the next semester class. So for plane motion only, we can simplify this vector triple product and can write it to be equal to minus omega square xy rho bar b relative to a. So how many terms are there on the left hand side here, right hand side here? You see 1, 2, 3, 4, 5. So that's why this term acceleration is called as a 5-term acceleration equation. So again, if you do not take into account the rotating frame, then you will see with respect to absolute, I mean to say non-rotating frame, you see your equation comes down to these two terms, because this omega xy, all these terms will not be there. So this will be brought down to this term, and again you know that this term will be having two components. One is the normal component, another is the tangential component, about which we have already learned and we have solved problems in our previous rotating frame, non-rotating frame, sorry. So this is what is called the more general 5-term acceleration equation, more general term for our body. So you know that the above equation is called a 5-term acceleration equation for plane motion. This is called acceleration analysis. The above 3-term and 5-term equations for velocity and acceleration are applicable to the problems involving relative motions as observed from a rotating reference frame. So that we need to understand. Now we further, this is about the theory that we need to understand. So we have 3-term velocity equation and 5-term acceleration equation, which we will be using for our problems, in solving the situations. So let's take first example from the textbook. This example is taken 5 by 160. It's an example taken from our Merriam-Craig book. And what you see here? You see here it is mentioned that disk rotates about a fixed axis through the point O. So this is the point O. About this fixed axis, the disk is rotating. It is rotating in the clockwise sense, but it is having an anti-clockwise angular acceleration. So through the point O, with the angular velocity omega, that is this omega is being given to be equal to 5 radian per second. So we write like this. This is 5 radian per second, and the alpha, that is clockwise, counterclockwise, is being given to be 3 radian per second square. So these values are being given. Now a small sphere A, so this is the small sphere A, right, moves in a circular slot. See, so the movement of this sphere in the circular slot, correct, while this disk will be rotating like this, will be the relative motion of this sphere with respect to this rotating frame, correct. So therefore the motion of this sphere in this slot would be the relative motion as seen in a rotating frame. However, if you stop rotating this disk, omega equal to 0 and also make alpha equal to 0, then the motion will be becoming absolute one. However, as you will be moving, you will rotate with respect to this, you will see that motion will be the relative motion as seen from the rotating frame. Now here, if we try to see the distance between these 2 points OA, this happens to be always constant because it is a circular slot. Had it not been a circular slot, suppose if this would have been a parabolic slot, it could have been a parabolic slot. So if this would have been a parabolic slot, this distance would be changing as well as the direction would be changing. So in our case, it is just the change in direction, because this distance between O and A is always going to be constant and it is equal to 15 inch. However, the direction of this line segment will change as the sphere occupies different locations on this slot, as seen from a person who is standing in an inertial frame. But A person who is standing and rotating with this frame will see that this sphere will be always in the same direction and at the same distance between them is there. It is same distance will not be the general case, but in this case that same distance will be there because it is rotating in a circular slot. But again, I am telling you, this problem may be there with you. Converting the geometry of the slot, instead of a circular slot, if you are given a parabolic slot, the equation of parabola of all these things are being given to you and you are asked to solve this problem, then always remember that you are also having this dimension to be variable in nature. Think of the fact how, say, after solving, showing you the explanation of the solution, think of how you are going to solve this problem if it is made a parabolic, if the slot is made a parabolic one. So in the direction shown at a certain instant, the small sphere moves in the circular slot at the same instant. And you see here, for the instant shown, beta is being given to be 30 degree. So all these are now instantaneous figures. Beta is equal to 30 degree, that you are going to get beta equal to 30 degree. Beta dot, all these are now instantaneous. Beta dot is 2 radian per second, 2 rad per sec. And beta double dot is being given to be equal to minus 4 radian per second square. That means beta dot is positive, that means it is moving in this direction, but beta double dot is minus, that it means what? That it will have the opposite direction vector, but we will come to them little later. First we try to do the velocity analysis. So first we write our velocity equation. Always remember that when you will be doing the analysis, first you need to write your governing equation, that what are the points with respect to which you are writing this equation. For example, here we are writing the velocity equation between the points O and the point A. Okay, that means the center of the disk and the sphere. We are going to write the equation between these 2 points, assuming that they are also a part of this body. So I see that our equation is something like this. This is V bar A equal to V bar O, that means this point's velocity, plus V bar A relative to O with respect to the rotating frame small xy, this rotating frame small xy, which is rigidly connected to this disk, correct? And then we have this extra term, that means omega bar xy cross the position vector of A relative to O. Now if you analyze these terms by terms, you will see the velocity of point O, that means this center point velocity of the disk, it is 0 because nothing is mentioned about the velocity of the center of the disk. So I can take this velocity of point A to be equal to null. So this is absolutely fixed. So we get this. Now we talk about this term, that means V bar A relative to O xy. So V bar A relative to xy will be equal to what? Now that will be equal to the relative velocity of this sphere as seen from this reference frame. So what relative velocity? That means suppose you are standing on this disk, what you will see? You are standing on the disk and rotating with the disk. What you will see? Now with respect to you, the sphere is changing its position as this angle beta is changing with respect to time. So therefore, this V bar A relative to OXY is basically equal to beta dot cross this position vector, because we do not have the change in magnitude of this vector. But for the parabolic slot, there would be another term added to it, right? That will take care of the change in magnitude of this distance. But in this case, that is not there. So only I need to take care of the change in direction, and change in direction is nothing but the cross product of the angular velocity cross this position vector A relative to O. So that is why here you see this V bar A relative to O. Here I put a star mark here, and I see this. This is the simplification. This is how we are calculating it. The magnitude of this vector will be, OA into beta dot. That means OA is how much? This is being given to be 15 inch, and beta dot is being given to be 2 radian per second. So 15 multiplied by 2 is 13 inch per second. So you see that we can write this in this manner, and this term we can take this thing common and can write that this will be minus 2, because beta dot is being given to be beta dot is in this direction, so it should be minus k cap, because k cap is anti-clockwise plus. So both the omega xy, these terms are, this omega xy is nothing but this omega bar xy is this one. This is your omega xy, because you are rigidly fixing this small xy onto this disk. So omega is basically equal to capital omega, xy is basically equal to small omega. So small omega is being given to be 5, and since this is clockwise, this beta dot is clockwise, so I have a negative sign here, k cap, and this position vector we write like that, and ultimately I find that V bar A is being given by, on algebraic simplification, we do it like this. So you see, we have approached this problem analytically, how to solve this problem. So this is an analytical method we are presenting. But the next problem that we will be going to show you will not be this analytical method, because I told you that analytical method has certain disadvantages for complicated problems. It is a simple one, so we can approach it analytically, and we can write that this will be our absolute velocity of this sphere, and I can say the absolute velocity is being given by this. And we can see from here, this is our velocity of the point A. Now we need to calculate the acceleration also, because we have to calculate the velocity and acceleration of the point A together. So we now go to the acceleration analysis. Again, write our equation. This is the full equation. Out of that, already we have explained that this should be null, and these are your Coriolis terms. Okay. Now you take one by one. So again, that problem has been shown here for your convenience. The same problem, same figure, same statement. I have repeated it here, and I find out all these terms separately. For example, first of all, I find out, you see, if you go term by term analysis, you see the 5 term analysis. First you are getting, because this O is null, so forget this term. So now it is 4th term. First is the relative acceleration of this point A with respect to O. So what this relative acceleration is having, it is having 2 components, as I have told you. This will be having 2 components. One will be towards the normal, correct, and another one will be towards the tangential direction. Now beta dot, you remember, beta dot is clockwise and beta double dot is negative, right? So therefore this acceleration, relative acceleration, is having 2 components. One is this red vector, which is acceleration of A with respect to O in the normal direction, and this is acceleration of A with respect to O along the tangential direction. So these are the 2 red vectors which takes care of the the tangential component and normal component, whose magnitudes are simple and can be found in this manner, correct? I hope this is understood. Now you have, you see, next term. What is the next term? The next term is the Coriolis component. Now you have to understand how you are going to get the Coriolis component of acceleration. So for Coriolis component of acceleration, we see that it needs to be crossed with the 2 things, that is, the angular velocity of the reference frame and the relative velocity of A with respect to OXY. Now you remember from the velocity analysis, the angular velocity is of course in the clockwise direction. So it is the clockwise direction. Angular velocity is in this direction. And the relative velocity, you see the relative velocity of A with respect to O was in this direction because your beta dot was clockwise. So therefore, if you see, this is a little bit, involved one. So beta dot, the relative velocity is in this direction and your angular velocity is in this direction. So what you need to do, you need to take the cross product of this vector. This vector means if you see it, in a three-dimensional manner. I draw it for three-dimensional manner. See, this vector, it means that it is vertically down. And this vector, you see that it is, say, this is z axis. Let us say this is negative z. And let us say that it is small x. So, you try to take the cross product of negative z x. So z cross x will be equal to what? Z cross x will be equal to y. Y means in this direction, right? But since you are having negative z, what will be the actual direction of the Coriolis? The actual direction of the Coriolis will be therefore in this direction. Please try to understand. This is your Coriolis direction because this is representing the relative velocity and this axis represents your omega xy. Omega xy. Sorry, this is omega xy. So if you take the cross product between this vector and this vector, your Coriolis will be like this. That means here your Coriolis will be coming towards the center. So you see this blue arrow. This blue arrow, it represents the Coriolis component of acceleration. What is the magnitude of the Coriolis component? That we can very easily calculate. The Coriolis component will be 2 omega xy into VA relative to OXY. So we have already found VA relative to OXY in the previous velocity analysis. Just multiply it and you get, this is the numerical figure. So the orientations of the vectors are most important here. So this is how you are getting the Coriolis component. In this manner, in this respect, I can help you by drawing a table. If you need to remember that table, correct? So how I can show that thing? Let us go to that page, extra page that I created here. Suppose you have, you consider 4 situations. This is 1, this is situation 2, this is situation 3, this is situation 4. All these are rotating rods, for example. All these are rotating rods. So these are all rotating rods. And I consider 4 possible combinations. First, I assume this is how it is in this direction you are having omega xy. Here I have, this is omega xy, okay? And here I have the slider. Let's fix the slider, sorry. Let's fix the slider. The slider is, it is like this. This is your slider. I just draw the sliders, 4 sliders here very quickly for you. These are your 4 sliders. And we can have the possibilities that this slider can have, this is the relative velocity. This is V rel, right, with respect to small xy. So this is, this arrow is in this direction. Here this arrow is in this direction. Now let us suppose this rod is rotating omega xy in this direction. This relative velocity is in the downward direction. Okay. And then we have, this is rotating in this direction, omega xy, and this is having downward direction. So These are only 4 possible cases of Coriolis. Now you analyze for the first one. This is omega xy, it is positive because it is coming outward from the plane of your figure. And the relative velocity is this, which means that your Coriolis component, I draw it with a black pencil, the Coriolis component will be this. This will be the direction of A Coriolis, A-C-O-R, I write. In this case, definitely, one of the factors is reverse. So Coriolis will be towards that side. So this will be your A Coriolis. In this case, again, one of the factors is negative. So your A Coriolis will be this. And in this factor, both the factors are positive, negative. So the product will be positive thus. And I can therefore say that this will be the direction of Coriolis. So if you remember these 4 figures, right, then it will be easier for you to interpret, right, to interpret your direction of Coriolis. For example, the problem that we are right now discussing, if you see that this problem, if you compare it, you will see that our case falls under this category. Because our relative velocity is outward, the angular velocity of the reference frame is clockwise. So ours come to this second category. So the Coriolis is inside. So you just see here, we have, the Coriolis here is inside. This is what you are getting. This is your Coriolis component. And similarly, you calculate the remaining components. Remaining components are very simple. Now collect them all and express them vectorially. It is a very simple task for you. Just collect all these terms, right? And then simplify, express them in I and j cap manner, and you will be able to establish that what will be your acceleration of the point A. That is the absolute acceleration of the point A. That means the absolute acceleration of the sphere, which is, having this relative motion inside this circular slot. So students, therefore, you can understand the analysis is little bit difficult, but you need to keep your cool and turn by turn, you need to evaluate all of them. But here, in this case, we have solved the problem completely analytically. Now, we will show you another example where, this problem will be solved in a semi-analytical approach. So this is a typical mechanism which is used in, you will learn in your machine tool application. This is a typical mechanism which is used in shaping machine or in quick return mechanism, Whitworth quick return mechanism. So this is actually called quick return mechanism. Part of it is not completely the quick return. There are other things are also there. But when you will work, fortunately for you, if the workshop opens physically, machine shop opens for you physically in the next year, I hope in the 3rd year you will be able to work on a shaping machine or in a planing machine. So there the mother mechanism is this one. The part of it is shown here. For completeness, you have other terms also, other things also, but I am not going into discussing that part. So this is a typical example of this. It is called quick return mechanism. Part of the quick return mechanism is shown here. What is the analysis of this? This OA is the main crank, and this is the slotted arm. Inside the slotted arm, there is a small sphere being carried. So you see here the crank OA. This is the crank OA. It revolves in the clockwise direction. This is the direction, clockwise direction, with a constant angular velocity of 10 radian per second. So it is a constant. I mean, it does not have any angular acceleration. For the position where theta is equal to 30 degree and the geometry is being given such that if this is theta, this is 2 theta, means at this instant, this is an isosceles triangle. But please remember, This distance AC is variable, but the distance OA and the distance OC are constant, and these two are equal, and naturally the angle will vary. So this is an isosceles triangle with OA equal to OC. For the position theta is equal to 30 degree, we need to determine the angular velocity of the slotted link CB and the acceleration of A as measured relative to the slot in CB. That means here what we are trying to calculate, and the acceleration of A as measured relative to the slot in the CB means what we are trying to get is acceleration of A relative to C as seen from the reference frame XY. So this is what we are going to calculate. But before that, we need to find out the angular velocity. So you need to do the velocity analysis first, and after that you will be able only to perform the acceleration analysis. So first write the velocity analysis. I take on the link CAB. First I consider this link CAB and write the velocity equation between the 2 points C and A. This is a rotating frame. You assume your XY frame to be mounted on this CB slotted arm at point C, and you are trying to calculate apply the equation between the points C and A on this link. So if you write, since the point C is immovable, so its velocity will be null, and I am left with only the two things. So for me, it becomes the velocity triangle. So if I see the velocity triangle, if we just note how we are trying to get this velocity triangle, you know, we have velocity of AC relative to XY, and we have omega bar XY cross rho bar A relative to C. Out of this, I do not know this term. I do not know this term, but I know its direction. This relative velocity must be along this slot. Either it will be in the upward direction or it will be in the downward direction, but it will be along this slot only. Okay. So, but this one I completely know, because I know the angular velocity of this theta dot, because angular velocity, you know, is a constant angular velocity OA. So it is 2 theta dot. 2 theta dot is being given for us. 2 theta dot is being given for us as 10 radian per second. So naturally theta dot, that means the angular velocity of this one will be equal to 5 radian per second. So omega bar XY is known to be equal to 5. Correct, 5 radian per second. And the position vector A relative to C is known. So I completely know this term. And what will be that? Now that term will be going to be perpendicular to this link AC, right? So the black vector AC, right? This black vector AC, this represents my this term. Okay, this represents my this term. And I have the relative velocity. Of course, what I can do, I can actually, through this tip C, I can draw a line parallel to this link, and it can go run like this. Okay. Beyond this, I do not know anything. Then, however, I know that sum of these two must be equal to velocity of point A. And what is velocity of point A? That is, of course, the point A is belonging onto this crank OA. So naturally, the point A's velocity is completely known to me, which should be tangential to this orange circle, and the magnitude also, because it should be, it should be equal to this 10 multiplied by this 0.2. That means it will be 2 meter per second. So AA is completely known to me. So AA is completely known. This is known, and the angle theta is of course also known to me. That is 30 degree. Because you know the angle between this line and this line, that means the angle between the perpendiculars. That means what I try to say, the angle between these two perpendiculars. This vector is perpendicular to BC and this vector is perpendicular to AO. So naturally, angle between these two perpendiculars will be the angle between the two lines. Since this is 2 theta, this is theta, this angle must be theta, so this angle must also be equal to theta. So I know therefore this angle as theta. So you see, from here I get, this velocity, and I can calculate that it should be VA equal to 10 into 0.2, that is 2 meter per second. And from this I can calculate what should be AC. AC is, the AC is AA cos theta. From here, omega CAB into AC is equal to AA cos theta, and omega, is being given here. Omega CAB is known to be equal to 2AA cos theta, and omega CAB is given to be equal to 5 radian per second. Either you can solve it in this way, or you could have solved it in a more straightforward manner. Here I have shown you the application of the triangle, but you could have established that it is 5 radian per second in a very straightforward manner, as I was telling, that 2 theta dot, this omega is basically equal to 2 theta dot. So since this is 2 theta dot, then theta dot must also be equal to 5 radian per second. You need not have to, solve this part. However, for the relative velocity, you need to draw this triangle. So you can verify that whether it is correct or not. That verification is also done here, but you could have avoided this part of the application. However, this relative velocity you need to find out. So the relative velocity, you can do it AA sine 30 degree. AA is known, that is 2 meter per second. So the relative velocity must be 1 meter per second, and that should be inside. See, I told you that the relative velocity could be away from C or towards C. In this case, it is shown that this relative velocity is towards C. So I can find out the relative velocity here. So the relative velocity is 1 meter per second, and that is being done. So I hope the velocity analysis is pretty clear to you. Now we are coming to the acceleration analysis, which is little bit cumbersome. You have to pay attention to the acceleration analysis. Again, I will be going in exactly the same manner we have done it for the velocity analysis. I first find out let's take the link CAB. So apply the 5-term acceleration equation between the 2 points C and A. So I have shown it. All terms I have shown it here. I am fortunate that the point C is having null. So I am remaining with 4 terms. 1, 2, 3, 4. 4 terms. Achha. That is one part. Another part is the acceleration of point A. This is also known to me completely. Acceleration of point A is because this crank is rotating with a constant angular velocity, the point A's acceleration will be always, the normal. That is, it will always be directed from point A to O. So acceleration of point A is given by this equation, which if you put the numericals turns out to be something like this. Very good. So now, after drawing all these things, after knowing all these things, now you start drawing the polygon. This is the polygon, correct? So first, I take the point A as my pole. First, I draw the red vector, which is acceleration of point A, which is known to me. That means AA. This is our AA. This is our AA. That first part I draw. After drawing this, let us now see what are the other things I know. And then I need to draw those known things. First you come the Coriolis. Yes, Coriolis I know. What will be the Coriolis? I'll come to later. But I think here shown first this term. I mean to say this term. This term. So I take first I have drawn this as number 1, the acceleration of point A. This I have taken as number 2. This omega square xy rho bar A relative to say minus. That means it will be towards this. So AC dash, you see AC dash, look at this figure. AC dash is equal to omega square xy rho bar A relative to C. Put the numericals, get the result. The numericals are straightforward to you. Rho bar A relative to C, how you will be getting this magnitude? It is simple. We have done it in the velocity triangle. Velocity triangle এ দেখো আমরা এটা বের করে ফেলেছি। কিভাবে বের করে ফেলেছি? The AC solve this triangle. হ্যাঁ, এখানে এই ডিসটেন্সটা 0.2, this distance is 0.2, this is theta 30 degree. So you can calculate how much should be AC. From the triangle, using the sine property or cosine property, you will be very easily able to get the distance AC, which is variable. But at this instant, this distance we can calculate. Very good. So AC is therefore known to me. So I know this vector. So I draw the blue vector. Acha. Then I take the Coriolis. Acha. তাহলে Coriolis কে calculate করতে গেলে I need to specify its direction. So how I am going to specify its direction? Look at your relative velocity sense and your angular velocity sense. Come here. See, this relative velocity is towards this. And what is the angular velocity? Angular velocity is towards this. So both are negative. You remember that 4 figures I have drawn. I come to again show you these 4 figures that I have drawn. See, this one is clockwise and this is coming inside. Both are negative, means Coriolis will be positive. So it will be towards your left hand side of the slider. Towards the left hand side of the slider. So come here towards the left hand side of your slider. Sorry, towards the left hand side of your slider. Come to the acceleration diagram. Towards the left hand side. See, towards the left hand side. So from C dash to C double dash, I draw this line C dash C double dash, which will be my Coriolis to omega xy V A relative to C xy. Now all these values are known to me. So I substitute, calculate, thereby I draw this. Beyond that, beyond C dash C double dash, I do not know anything. Correct? So what I do not know, therefore let us try to identify. So this is our third term that we drawn. This is the third term we draw. This is the first, this red line. This is the second, this blue line. This is the third, the green line. Now we do not know which. I do not know this. I do not know this. So cross terms are not known to me. What I will be doing? First, I see acceleration of A relative to C xy. At least this much is known to me, that maybe I do not know this, but at least this is known to me that it should be along this AC slider, because this is the relative velocity of this. So the relative acceleration must also be along this. So either up or down, I do not know. So what I do, I draw this blue line, both in this direction, correct? Because I do not know which way it will be, either plus or minus. So through the tip of C double dash, I draw this line which is parallel to this line, right? So this part is therefore drawn. Then comes this, which is, perpendicular to this AC line. It is omega dot xy rho bar A relative to C, means it is the tangential component of acceleration of this rotating frame. So what will be that? That will be going to be perpendicular to this blue line. So through this tip, through the other tip, draw a line, black line, which is going to be perpendicular to it. So draw these two and allow them to intersect at point C, and then put all the arrows to complete your triangle. That sum of all these 4 terms must be equal to the acceleration. So you see this plus this plus this must be equal to this. So you can understand from here that your relative acceleration is away from C and your tangential acceleration, angular acceleration of this link will be in the clockwise direction, because you see this is moving up. That means mentally, if you put this vector at this point and give the arrow, it will show that this will be rotating in the clockwise sense. So I can therefore find from this diagram that the relative acceleration is away from C and the angular acceleration of this link must be in the clockwise direction. So these two conclusions are drawn, but I do not know their magnitudes. So I identify them. This is one unknown and this is one unknown. So what I'll be going to do, I'll be taking any one, say for example, my objective here is to find out what? My objective here was to find out two things. Determine the angular velocity of the slotted link, which we have already done, and find the acceleration of A measured relative to the slot in CB. Okay, so we need to find out, our objective is to find out this one. Our objective is to find out this blue vector. This C double dash C is our unknown, desired unknown. So this is not they have asked. That means they have not asked the what is the angular acceleration of this slotted link. I will put this to your homework. Solve this to find out the angular acceleration. However, I have not solved it here because my objective is only to find out the blue vector. So what I do, I will take the components of, take the projections of all the vectors perpendicular to this unwanted unknown. This black vector is unwanted unknown. All right. We are not interested to get the angular acceleration of the slotted link. But the full question here, Miriam's question will be modified by DN sir, and the question will be that you need to find out both the unknowns. So that's why I 50% solve it for you, following our great teacher Miriam sir, and I will ask you to find out this black vector at your home. So since our objective is to find out the blue vector, I take the projections of all these vectors along the line MM. So it means the projection of this red line on this should be equal to sum of the projections of this one and this one. Correct? Because these two are perpendicular. So I am very relieved they are not coming and hampering me. So therefore, I can write the projection of this red vector on this line must be equal to this vector minus this vector. Because if I call this is plus, you see the projection is downward. This red vector projection on the line MM is downward. So downward direction I take plus. So it will be therefore plus and then it will be minus. So exactly, I hope that I have solved the problem in that way. Yes, I have taken the projections of all vectors along this and you see A cos theta, AC dash minus CC double dash. Now you put everything, get your result. So you see that involvement, drawing of this particular, the drawing of this particular acceleration diagram is little bit difficult, but you need to keep your cool and simply just methodically, I have given you the algorithm. First, try to locate the known vectors and then start drawing the known vectors through the pole. Say here, I have drawn this known vector through the pole. I know I could have started with this vector also. I mean to say, since the Coriolis is also known to me, so I could have started with the Coriolis as well. So here I have not started with the Coriolis. I have started with the normal component of acceleration. See this one, the normal component, but it could have been rearranged. So that rearrangement, I think you should do at your home with your experimentation. That means do not copy my figure, just try to redraw them by permutating. That means you see this is 1 I have drawn. Now you interchange these two, 3 and 4. I first draw 3, then I draw, sorry, first draw 2, then I draw 3. Interchange them, see how your polygon looks like, whether you are able to locate all the vectors or not. This you should experiment, and then only you know you will be having your concepts clear. And again I am telling you, solve 2 to 3 problems from this chapter, particularly doing velocity and acceleration analysis both, so that the thing becomes completely defined for you, so that in the examination, during the examination, you do not have to fiddle around যে কিভাবে করব কোনটা দিয়ে আগে শুরু করব. This you should not have this this kind of hitchkitch within your mind. So that hitchkitch you can remove very easily if you solve at least 2 to 3 problems from this book, taking separate problems, right? Do not go for very tough ones, because complicated figures we cannot give you within the stipulated time. However, if the examination is 24 hours, then no guarantee for the toughness of the question is from that is I need to be very clear. তুমি যেই সময় বাড়াবে কোশ্চেনের টাফনেস কিন্তু বাড়তে শুরু করবে. সুতরাং ওই রকম করে বললাম আর কি, যে মিডিয়াম ডিফিকাল্টি সাম যেগুলো আছে সেগুলো 2 থেকে 3টে করো. কেউ যদি মনে করো যে আমি 3টে না আমি 4টে করলে আমার পক্ষে সুবিধে, 5টা করলে সুবিধে, অলওয়েজ ইউ আর অলওয়েজ ওয়েলকাম. বাট অ্যাট লিস্ট মিনিমামটা আমি যেটা বলছি, প্রত্যেকের যেটা I should advise that at least 2 to 3 problems you should solve here, so that you can actually define the algorithm for you, so that you don't have any kind of ambiguity within yourselves. So আর এই যে বললাম যেটা এখানে আমি অর্ডারটাকে চেঞ্জ করতে পারতাম, আমি এখানে ব্লু ভেক্টরটাকে আগে ড্র করেছি, নন ভেক্টরগুলোকে আগে ড্র করতে শুরু হবে. তাহলে নন ভেক্টরগুলোকে আইডেন্টিফাই করতে হবে, আননোন ভেক্টরগুলোকে আইডেন্টিফাই করতে হবে, এবং তারপরে দেখো ড্রয়িংটা কিন্তু ভেরি সিম্পল. এটার মধ্যে কিন্তু কোনো জুজু কিন্তু কিছু নেই. অনলি থিং that you need to approach the problem in a sequential and a systematic manner, এবং সেটা তুমি তখনই করতে পারবে when you solve certain problems you do by yourself. যেমন এই এখানে বললাম যে বাড়িতে you should try to actually, এখানে দুটো জিনিস দিলাম, একটা হচ্ছে ফাইন্ড আউট দিস ব্ল্যাক ভেক্টর, এটা বের করো. সেকেন্ড দিলাম যেটা, সেটা হচ্ছে যে আমি যদি অর্ডারটাকে চেঞ্জ করে দিতাম, অর্থাৎ আগে ব্লু ভেক্টরটাকে না ড্র করে আগে যদি কোরিওলিসকে ড্র করতাম, হাউ মাই অ্যাক্সিলারেশন ডায়াগ্রাম উড লুক লাইক, সেটা তো কেউ করতেই পারে না, কারণ দুটোই তো তার কাছে নোন, এই দুটোই তো তার কাছে নোন. সুতরাং 3ও জানে সে, 2ও জানে সে, কোরিওলিসও জানে সে, এই নরমাল কম্পোনেন্টও জানে. সুতরাং হি ক্যান অ্যাপ্রোচ উইথ এনিওয়ান. তাহলে সেইটা করবার জন্য হাউ ইওর ডায়াগ্রাম উইল লুক লাইক, এইটা কিন্তু তোমার নিজের, ইউ শুড হ্যাভ দ্যাট হ্যান্ডস অন এক্সপিরিয়েন্স যাকে বলে, that hands-on experience you must have. ঠিক আছে? So with this we come to an end of today's class. Before the Diwali break, we finish the Coriolis, I mean to say the relative velocity method, both the non-rotating frame and the rotating reference frame. After the break, when we will meet, we will take up the last method, which is, I have already told you that that method is specific for velocity analysis. It cannot be applied for the acceleration analysis. That is known as the instantaneous center of velocity method. আমরা একটা অঙ্ক একটু কঠিন, সেই অঙ্কটা ইচ্ছে করেই আমি বেছেছি ওই রকম, কারণ একটাই অঙ্ক দেখাবো যার মধ্যে all complexity I need to show. So for that I have selected one problem from the book of Merriam and solved it for you, and I will explain the method in the next class when we will be meeting. Okay, so at this point I stop my recording and open this discussion for any question or any doubt you might be having. Feel free to ask me. বলো বাবু, কারো যদি কোনো কোয়েশ্চেন থাকে, feel free to ask me. আর না হলে তো আমি এটা তোমার এতে পাঠিয়ে দেবো, ক্লাসের নোটটা পাঠিয়ে দেবো. আচ্ছা, ক্লাসের রেকর্ডিংটা তোমরা কেউ করেছো?
হ্যাঁ স্যার।
বাহ, ভেরি গুড। তাহলে সেই রেকর্ডিংটা ভালো করে শোনো আর ক্লাসের নোটটা দেখো। হ্যাঁ, আমি আজকের ক্লাসের পরেই আমি এটাকে পিডিএফ করে তোমাকে পাঠিয়ে দিচ্ছি, গ্রুপে দিয়ে দিচ্ছি। সো ফ্রম দেয়ার ইউ ক্যান গেট ইট।
ওকে স্যার।
ঠিক আছে? আচ্ছা, এ আছে আমাদের বিশাল বাবু আছেন? হ্যালো বিশাল।
গেস ও হয়তো জয়েন করেনি আজকে।
আজকে বিশাল জয়েন করেনি, আচ্ছা আচ্ছা, ঠিক আছে, ওকে। না, আমি যেটা বলছিলাম যে আচ্ছা, বিশালকে তাহলে একটুখানি ফোন করতে হবে আমাদের। ওকে, ঠিক আছে, আমরা তাহলে দেখে নিই। আমরা তাহলে তোমাদের যদি কোনো প্রশ্ন না থাকে তাহলে আমি এখানে প্রেজেন্টেশনটাকে স্টপ করছি। এটা একটু অবশ্য মানে এক্ষুনি মানে বাড়িতে তোমাকে ভিডিওটা ভালো করে দেখতে হবে এবং হচ্ছে যে নোটটা যেটা পাঠাবো সেটা ভালো করে পড়তে হবে, দেখে বুঝতে হবে। কারণ এই রোটেটিং রেফারেন্স ফ্রেমের অ্যাক্সিলারেশনটা একটু বড়, একটু দেখলে একটু কিরকম ভয় ভয় লাগে, কিন্তু জিনিসটা কিন্তু খুব সোজা। মানে তোমাকে ওই সিকোয়েন্সিয়ালি এবং সিস্টেমেটিক, ওই বারবার করে যেটা বলছি যে সিস্টেমেটিক্যালি তোমাকে হচ্ছে এটাকে অ্যাপ্রোচ করতে হবে, না হলে পরে কিন্তু ওটা হচ্ছে তোমার গুলিয়ে যাবে। বুঝতে পেরেছো?
হ্যাঁ স্যার। থ্যাংক ইউ স্যার।
ঠিক আছে, ওকে, ঠিক আছে, তাহলে চলো আজকের মতো।
থ্যাংক ইউ স্যার।
হ্যাপি দিওয়ালি টু
হ্যাঁ স্যার, হ্যাপি দিওয়ালি। ভালোভাবে স্যার সেলিব্রেট
হ্যাপি দিওয়ালি স্যার।
হ্যাঁ, সেফলি করো। এখন আবার তো গ্রিন বাজি ফাটাতে বলছে, কোনো রেড বাজি ফাটিও।
হ্যাঁ
আছে, কোনো রেড বাজি ফাটিও না, গ্রিন বাজি ফাটাও।
ঠিক আছে,
ঠিক আছে, ওকে, থ্যাংক ইউ।
ঠিক আছে স্যার, রাখছি স্যার তাহলে। হ্যাঁ স্যার।
হ্যাঁ, চলো। আজকে কি আর ক্লাস আছে তোমাদের?
হ্যাঁ, তারপরে মেশিন ড্রয়িং। হ্যাঁ হ্যাঁ,
ও আচ্ছা আচ্ছা
তারপরে আমাদের B2 তে মেশিন ড্রয়িং, আর তারপরে একটা ফ্লুইডের টেস্ট আছে সিটি।
আচ্ছা আচ্ছা।
তারপর
মেশিন ড্রয়িং কি
তারপরে
তোমরা
নর্মাল।
মেশিন ড্রয়িং কি তোমরা ক্যাডে করো?
না না, এখন অব্দি ক্যাডে করিনি ওই জিনিসটা।
হাতেই করো, হাতে করো নাকি?
হ্যাঁ, হাতে কলম।
আচ্ছা,
একদম, মানে ওই যে লেআউট, ওই হ্যাঁ ছবি তুলে টিকেবি স্যারকে পাঠিয়ে দিই আমরা, মানে ওরকম ভাবেই করি। টি স্কেল বগেরা যেরকম হয়, যেরকম ভাবে করতে হয়, জাস্ট এখানে উইদাউট প্রফেসর আছে তো ওইটাই আর কিছু নেই।
আচ্ছা, মানে তোমরা কি ধরো, আমি জাস্ট একটা মানে জিজ্ঞাসা করছি কারণ আমাকে আবার সামনের সেমিস্টারে ফার্স্ট ইয়ারে ড্রয়িং নিতে হবে।
আচ্ছা আচ্ছা, হ্যাঁ
জিজ্ঞাসা, মানে তোমরা কিভাবে করছো বলো তো? তোমরা কি মানে ধরো একটা ড্রয়িং শিটে তোমরা ড্রয়িং করলে, ঠিক আছে, এবার ড্রয়িংটা করার পরে মানে টপ ভিউ, ফ্রন্ট ভিউ, সাইড ভিউ এগুলোর কি আলাদা আলাদা করে ছবি তুলে তারপর সেটা পাঠাচ্ছ টিকেবি স্যারকে?
না স্যার, বলতে গেলে
একটা শিটেরই ছবি পাঠাও, কিন্তু সেটা তো অনেক অনেক মানে সেটা তো অনেক ছোট হয়ে যাবে গো। মানে তোমার ক্যামেরাতে কি, তুমি তো ফোনের ক্যামেরাই ব্যবহার করছো নিশ্চয়ই?
অবশ্যই, কিন্তু স্যার এই অ্যাডব স্ক্যান থেকে যখন আমরা স্ক্যান করি না, তখন মানে ডাবল ট্যাপ করলে ওটা ইজিলি আপনি দেখতে পাবেন, ছবিটা ফাটবেও না। মানে ব্যাপারটা হচ্ছে আমরা ডকুমেন্ট ফরম্যাটে যখন পাঠাবো তো আপনাকে,
আচ্ছা, পিডিএফ করে পাঠাবে তাই তো তুমি?
হ্যাঁ পিডিএফ করে আপনাকে পাঠিয়ে দেবো, তো অসুবিধা হবে না। তো আপনি ওটা মানে গুগলে একটা ক্লাসরুম বানিয়ে নেবেন, তো ওখানে বলবেন বাচ্চাদেরকে দেওয়ার জন্য, তাহলে কি হয়ে যাবে, ইউ উইল বি এবল টু কিপ আ ট্র্যাক যে কারা দিচ্ছে, টাইমের মতন দিচ্ছে না, সেটা ডেডলাইনও সেট হয়ে যাবে। সো ইউ ক্যান ইজিলি কিপ আ ট্র্যাক অফ দ্যাট।
গুগল ক্লাসরুমে ইয়ে করতে হবে এমন তো আমি গুগল ফর্মেও দিয়ে দিতে পারি।
হ্যাঁ, যেটা এবার আপনারা ব্যাপারটা হচ্ছে গুগল ফর্মটা তো আপনি কি অতদিন ধরে খুলে রাখবেন, মানে তার থেকে ভালো না যে ক্লাসরুমে আপনি ডেট আর টাইমটা দিয়ে রাখলেন, যে লাইক সাপোজলি 3rd নভেম্বরের মধ্যে ডেডলাইন, 3rd নভেম্বর রাত 12টা অবধি, এবারে 12টার আগে অবধি যতজন ছবি তুলে আপনাকে পাঠিয়ে দিলে হয়ে গেল। বা যারা দিল না, ইউ উইল বি এবল টু কিপ আ ট্র্যাক, মানে এটা গুগল অটোমেটিক্যালি ট্র্যাকটা আপনার জন্য বের করে দেবে যে দিস পিপল হ্যাভ সাবমিটেড লেট, সো ইউ ক্যান ইজিলি ইভ্যালুয়েট দেম অন দ্যাট বেসিস। তো আপনি ওরকম ভাবে মার্ক করতে পারবেন। সো লাইক ক্লাসরুম সিস্টেমটা বেশ ভালো আছে এখানে দেখতে গেলে।
তাই না? আমি অবশ্য গুগল ক্লাসরুমটা ট্রাই করিনি।
আচ্ছা আচ্ছা, আপনি এটা দেখবেন স্যার ওটা। আর স্যার প্রেফারেবলি একটা জিনিসই বলবো যে মানে জানি না জিনিসটা কিরকম শোনাবে, মানে আমি একটা স্টুডেন্ট হয়ে বলছি, মানে স্যার ওদেরকে বলবেন যেন ওটা সবসময় যেন মানে যেইভাবে আমরা সবাই শিখেছি, মানে টি স্কেল, সেট স্কোয়ার নিয়েই যেন বসে যেন সব ডায়াগ্রাম করে, মানে এরকম নয় যে পেপার অ্যাভেলেবেল নয় ইনস্ট্রুমেন্ট। হ্যাঁ, মানে
ফ্রি হ্যান্ড কেউ যাতে না ফ্রি হ্যান্ড করলে তো সেটা আটকে যাবে, তার তো প্রজেকশন।
অবশ্যই অবশ্যই, হ্যাঁ। আর মানে ব্যাপারটা হচ্ছে যেন পেপার সাইজ গুলো যেন ওরকম ভাবে ইউজ করে।